We ended last time with a discussion of electrons and how these things line up. We're going to do a quiz today, but we'll do it in a little while, so we have some time to review, and there's a couple people who can't be here right away today. So as hopefully you know, the first exam is next week, so that'll be Monday instead of lab. So there's no lab, there's no pre-lab. It'll just be go upstairs and have the exam. The exam will cover chapters 2, 3, and 4, so all the stuff we've already talked about. Unit conversions, then energy, which is energy and matter, which is what we'll be doing the quiz on today, and then the atoms and elements stuff that we've been working on for the last week, and with counts of particles, neutrons, protons, electrons, and symbols and atomic masses and isotopes and all that kind of stuff. So that will be that. Any questions about that? Yeah.
There's study guide for that at all?
What do you mean?
Just for the exam.
Yeah, I mean everything that's on there is in those on Blackboard, and if you look at each of those units, there's like a list of 10 to 15 things that you should be able to do for each chapter.
Oh.
So just use that. Yeah. Oh. Yeah, use that. The exam will be written based on that, so I'll be looking at all those things. And, but then in terms of actual practice, like to do well in the exam, is homework. So do all the suggested homework problems from those 3 chapters for sure, if you haven't already. Mm-hmm. Yeah, either online or on paper, depending on what everybody's doing. So that's definitely the way to do that. There's not going to be anything on the test that isn't similar to homework problems. So if you've done all the homework, you've seen whatever is going to be on the exam. All right. So that said, I wanted to spend a little time here kind of going through some of the stuff we've talked about already, a little bit of a review. This is kind of your last chance to ask some questions here in class before the exam on Monday. So particular topics that you're having trouble with or things that you want to go over again. Anything in particular?
With the exams like next Monday?
Yeah. I think, right? Unless I got that wrong. Yeah, we have, so class is Monday, or class is Wednesday, so the exam will be upstairs on Monday. Yeah. Exam's always during the lab times. Definitely bring a calculator for that. I may be able to find some calculators upstairs, but it's not always, they don't always work, and we don't always have enough, so make sure you bring your own calculator. You're going to definitely need it for this exam. All right, so I guess nobody has anything in particular they want to talk about. Yeah?
Can you do the temperature change?
Yeah. Good question. So let's say you have some water that's heated from 25 degrees C to 78 degrees C, and let's say you have 150 milliliters of water. Like that kind of a thing. So you got 150 milliliters of water that you heat from 25 degrees C, around just above room temperature, up to 78 degrees C. How much energy is absorbed? Anybody know how we do this or what this involves? Right, so this is really a question that's asking about specific heat. So how much energy does it take to increase each gram of water's temperature by 1 degree? We know that for water, the specific heat is 1 calorie per gram degree C. 1 calorie per gram degree C, which means every calorie takes 1 gram of water, increases it by its temperature by 1 degree C. So how do we know how many grams of water we have?
150 milliliters.
We have 150 milliliters of water, but we need mass. So how do we get that? Right? So how do we get from a volume to a mass? What? Yeah. What kind of a quantity relates volume and mass? Yeah, well, grams is the mass, and volume's in milliliters, so how do you know how many grams are in a milliliter? Yeah, it's actually somewhat simple for water because what we're talking about here is the density. So what is the density of water? 1. Yeah, but what's the unit? 1 gram per milliliter. So every milliliter of water weighs 1 gram. Every gram of water weighs 1 milliliter. There will definitely be plenty of density on this exam, so make sure you practice a lot of those problems. So if we know the density of water is 1 gram per milliliter, then we know that 150 milliliters of water weighs 150 grams. If we want to do it, I mean, this is a little bit overkill, but just to show how it works, 150 milliliters of water, if you really want to do a whole conversion thing, times 1 gram of water per 1 milliliter of water is 150 grams of water. So that's not, you don't really need to write that out for water because it's just 1. But if you were dealing with something else, like a metal, you would have to use the density to figure out actually how much you had. If you were given a volume, or if you were given a volume and you needed a mass. All right. So now we have mass, and we have the specific heat. And the last part we need is the temperature change. That's that delta T, or the change in temperature. So the change in temperature there is 53 degrees, right? All right. So we've got 150 grams of water moving up 53 degrees. 150 grams of water times 53 degrees C times the specific heat, which is 1 calorie per gram degree C. Grams and degrees C cancel, and we're left with calories, which is, maybe got a calculator handy? So it takes 7,950 calories of energy to move that much water by that temperature.
Would you call it specific heat from something else? I don't see what define specific heat. I don't know. You
Yeah.
tell us the number, right? So we can find out.
Yeah. Well, we could go one way of that. Yeah, certainly if it was a similar question, but I gave you copper or something instead, I would say, okay, here's the specific heat of copper. I think there's a question in the book, one of the homework problems. It's a little bit confusing, not confusing, but it's a little tricky because it does all these parts with water. It's like A, B, C, D, all water, and then all of a sudden the last one is with copper. So you have to look up the specific heat of copper to actually get that one. But I would give you those numbers if you need them. While we're talking about this, another thing that you can use this for is you can actually calculate specific heats of some. So let's say we have some unknown substance X, right? Something. We don't know what it is. We don't know what it's made out of. But we need to know the specific heat of it to figure out how it's affected by energy, how much energy it requires to change its temperature. So one thing we can do when one thing we can measure with that is we can take the mass of that substance. So let's say we have 150 grams of substance X. And let's say we measure it, or we again move it 53 degrees from from 25 to 78 again. And then we actually use another instrument to measure the energy input. So we actually measure the energy. Let's say this time we get 5,000 calories. So we use some device to measure, or we use a special heater that actually measures how much energy is being put into this thing. Well, if we do that, we can actually find the specific heat for the unknown compound. Because it's the same equation, we have to multiply those things by the specific heat. If we have some unknown substance, we can solve for the specific heat by dividing 5,000 by the product of 150 and 53 and find the specific heat for the substance. Now, this is not something that I would ask you on the exam. It's a little bit beyond what we do here. But just looking at that, comparing it to water, would you say that substance X has a lower specific heat than water or a higher specific heat than water? Why lower?
Because the outcome is not as high as the 7,950.
Right. So for this, exactly. For the same mass and the same temperature change, it takes less energy to do that. And that means the specific heat must be lower. Or if you'd like to look at it from a math perspective, these things multiplied by something, if you want to make a lower number, that something has to be lower than 1 to make the lower number. Right. To actually solve for that, you would multiply these two together and then divide 5,000 by that number, and that would be your specific heat. That's a nice thing about stuff like this is you can use these to find out new information. You can also use it to calculate heat from known substances. All right, is that help? Yeah. Okay. What other kinds of things have you been having trouble with in your homework over the last couple of weeks? Anything in particular? Well, let's look at some of this atoms stuff because that's the most recent. We've done a lot of these kind of fill in the tables. We did it in lab. We did it in class last week, I think. And that's probably something that's going to show up as well. So let's look at some of those, or something like that. So if I told you that you had an atom with 12 protons and 14 neutrons, how would you write the symbol for that atom? And since the neutrons are specified, make sure to specify the isotope as well. So how would you write that down? An atom with 12 protons and 14 neutrons. Just like, I know we had to do a bunch of these on Monday in lab. There was that whole big table. Yeah.
FE.
Why FE? How'd you figure out FE?
24 with 14 to 12.
Okay, so if you add those together, you get 26. And so FE is element 26, so that's what it is? Everybody okay with that?
Whatever 12 is on there, the number.
12?
Number, so be there.
Yeah, how do you determine, so you're saying it's just the number of protons?
The atomic or the number of protons is the atomic number.
Yeah.
Which should indicate what element or atom. Yeah.
Right. So this should be magnesium because the number of protons gives us the atomic number, not the total number. The total number is what? What's that called? The mass, the atomic mass. So how do we denote that? Right, we write it up in the upper left-hand corner here. So this would be 26, magnesium 26. All right. How many electrons would this atom have? $12? How do you know? Yeah, assuming the atom is neutral, you got to have the same number of protons as electrons. So then, how many valence electrons? How'd you get 2?
Second row.
Yeah, because you look and it's in the second column, it's in column 2A. So you got 2 valence electrons and 10 in the core.
In the second group, right?
The second group, right? Or family, or column.
Period is how many electrons it has.
Periods are the rows.
But I mean, like, what does the period count? Like, what's that for? You know?
Just which bucket it's in. So you got the first period, hydrogen and helium. Those have their electrons in the first bucket. The second period, first and second. The third period. So yeah. So which bucket the valence electrons are in. Like everything in column 2A has 2 electrons, but in beryllium they're in the second shell or the second level. In magnesium they're in the third level, and in calcium they're in the fourth level, and so on. So that's what the period tells you. All right, let's try another one. Let's take an isotope, a specific isotope. Calcium 46. And let's get the proton, neutron, and electron count for each, for that isotope, for an atom of that isotope.
I have a quick question regarding the last question. After like 26 magnesium, do you write underneath the 26 the number of electrons?
No, but sometimes you write the atomic number down here. So sometimes you'll see the atomic number down here, which is also the number of electrons. But
would you expect us to write down the test?
it doesn't matter to me. It's redundant because the magnesium already tells you that it's 12. You know, because the only possible number that this could be, if it's magnesium, is 12. So it doesn't need to be there. If you like to put it there, that's fine. When we do nuclear reactions in a few weeks, it can be useful to have that down there because those numbers will actually change in a reaction. Yeah, good question. All right, so calcium 46. What kind of numbers do we have there? 17, 29, 17. Anybody get anything different? All right, how did you get those?
To find the neutron, you just take you subtract 46 by the atomic number, which is 17.
How'd you find the atomic number?
Because find the proton, it's just you just look at one.
Okay, so you have to look up calcium. If you didn't know the symbol for it, don't forget on the exam you'll get a periodic table that has the names. So
And the numbers?
And the numbers.
Oh.
Yeah. So you don't need to know the symbols, but you would look it up and say, okay, calcium, that's Ca. Look at the periodic table, and you see that Ca is 20. So what should the number of protons be? So then does that change how you calculate the neutrons?
Yeah, I looked at the wrong.
Okay, so you went with Cl. What is Cl? Do we know? Chlorine. And there's a lot of them like that it seems like one should be one symbol or another, so just, look it up to make sure so you don't.
What is 20, 20, 20? No.
So
So yeah, 16.
There we go. So now we can fill that in. All right, does that look better? Thanks for volunteering your answer though, because that's totally a common thing to do. There's a bunch, well, let's see what else we've got that people always mix up. Well, boron, so there's boron, bromine, barium, and those are all different, so it's easy to mix those up. But yeah, or there's actually IR, which is iridium, but people say that that's iron. So we get that. There is antimony is SB, number 51, but people say it's AT, which is 85, which is acetine. So you don't have to remember these. Just look them up if you're not sure to make sure that you get the right symbols. All right. So you feel sort of good about this kind of thing? Sure.
Can you give us like questions on the test?
These are questions on the test.
Oh, they are?
I mean, no. They're they're very similar. I mean, they'll be the same types of things. Seriously, if you go through and do all the homework, that's pretty much. There's not going to be anything in the test that's that different. Because how many ways can I ask you how many protons and neutrons and electrons are in things? There's only so many ways I can, put that in there. Let's try another one. So here is one that might mess you up in a test environment. So I've seen this happen before. What is the atomic mass of a chlorine atom with, let's say, what is the atomic mass of a chlorine atom with 18 neutrons? So if you don't have a periodic table with you, as we just discussed, chlorine is Cl. So what do you think? What's the atomic mass of a chlorine atom with 18 neutrons? What? 26? Any other numbers? Anything different? 53? Okay. What else?
54.
You have 54. Okay. What? You're going with 25? 35? And we'll change yours to 25? Oh, you do want to change it to 35? Okay. Any other ideas? Other answers? All right, why 35? You both said 35.
Well, I add the number of neutrons
Mhm.
with the number of protons that the chlorine has,
Okay.
which is 17.
Okay.
Those 35.
All right, thanks. 53 or 54, where do those come from?
I added mass to 18 neutrons.
Yeah.
Okay,
Yeah.
so you added,
I round my 35.45. I think to just 35 plus 18.
okay, and then so then you get 53 or 54?
Even the mass, the protons plus neutrons.
Right.
So I did too.
So actually, the right answer here is 35. But it's a common issue. If this chlorine atom has 18 neutrons, that means it also has 17 protons, because we looked that up. And so the atomic mass is the neutrons and the protons, which is 35. But that's a common mistake, is looking at the periodic table and using the number in red. Remember that the number in red on the periodic table, that mass on the bottom, is an average. An average of all the isotopes that exist. And when we start doing calculations in a couple chapters, when we deal with actual lab calculations of how much to weigh out, we'll use those numbers. But when we're talking about individual atoms, we're just talking about the protons and the neutrons in the individual atoms. So that's why you get 35. So this isotope would be chlorine 35. Yeah.
So what's the difference between mass number and
Nothing. They're the same. It's the same thing.
when I think of atomic mass, I'm thinking of the bottom number.
Yeah.
So when I'm thinking of mass number, I'm thinking of.
Number on top.
Right.
Same.
No, they should be the same. They should refer to the same.
When you say it should be the same, is it the one up or the one down?
You mean I'm talking about the periodic table.
Yeah.
The number below there, that is a mass, but that is an average of the mass of all the isotopes that exist. So if we look at chlorine, for instance, it's 35.4527. That's because most of the chlorine around in the world is chlorine 35, and then there's also some chlorine 37. And you average those together and you get something a little bit bigger than 37 or 35. But if we're looking at just one atom of chlorine, it's either 35 or 37. It's not a fraction. There can't be any decimal or fraction when you're just counting protons and neutrons. So it's true that the actual mass is a little bit higher than 35 because of the electrons and all of that, but we call it 35. We count the protons, and the neutrons, we add them together, we get the mass.
So you just take the atomic number minus the AT.
Right. Because that would be the protons and the neutrons added together.
But if you gave us a specific isotope, then
Yeah.
you would be asking us about the bottom or something.
No, if we wanted to, we haven't really worked with the bottom numbers yet. Later, we're going to say, okay, if we need to weigh out a gram of chlorine, how many actual chlorine atoms is that? We're going to need the bottom numbers for that because then it's an average of everything. But when we're talking about individual atoms, we're talking about protons and neutrons adding together to make the atomic mass. And that's precisely why I asked this, because if I ask this problem on an exam, I know that I'll have people that write down 35.4527. Right. So I'll say, oh, atomic mass of chlorine. I'll go look for chlorine. I'll write down the number that's right there. And that's not correct, because I'm asking you about the atomic mass of a specific isotope, the specific one with 18 neutrons. All right, so for a little bit of vocabulary, I'm going to put down four elements here. Now this time, without looking at your fancy periodic table, let's just look up there. Which one of these is an alkaline earth metal? Be. Okay. Anybody disagree? Be. Agreed. Also Be. All right, everybody agrees. Yes, that is the alkaline earth metal is Be. How do you know that? Yeah, there's no fancy special way to figure that out. You just got to remember those categories that we talked about. So the second column, the second group, the second family is the alkaline earth metals. All right, which of these four are not metals? Which are non-metals? Nitrogen and fluorine. All right, how'd you know nitrogen and fluorine are not metals?
Because of where it's on the other side.
Yeah, because they're all, everybody kind of pointed. They're on the other side of the dark line, right? Yep, that's all there is to it. All right, I think this is going pretty well. Thank you. You got this. So keep working with your homework. Keep working on it, and let's go back and talk a little bit more about the electrons. So, if you remember, back to last week. Anybody remember last week? Or is it just gone? At the very end, we started talking a little bit about electrons. We put them in these groups, and we talked about valence electrons versus core electrons. And then at the very end, we started thinking about what would happen if you lost some electrons. And we found that if you lose some electrons, you get a different number of valence electrons. You see that? So here's magnesium with its 12 electrons and its 2 valence electrons. If we lose those 2 and we become a magnesium 2+ ion, we now have 8 electrons in the valence shell instead. And that turns out to be important. You know why that's important? Right here, or remember? Or, I don't know if we said it or not, but we kind of ran out of time.
The shell's full, the atoms complete.
Yeah, the shell is full. There's a special stability to a full shell. So let's start anew here. There's a special stability. So this thing is especially stable, low energy, happy, however you want to describe that. Special stability when the valence shell is full. Meaning usually how many electrons make a full valence shell for most of the shells? Yeah. Hydrogen and helium don't get 8 because they're in that first shell, so they can only have a max of 2. But all the other ones, we can say 8. And actually, that gets a little bit tricky when we talk about the transition metals, the metals in the middle. So this is really just for the first 2 columns, and the non-metals. They kind of work. The transition metals kind of work like this too, but it gets a little bit trickier. So we're not really going to get into that. But we have the special stability when the valence shell is full. It's usually 8 electrons. Anybody know what that's called? This rule that valence shells want to be full of 8 electrons. There's a name for it. I don't know if you've heard it before. Yeah. It's called the octet rule. Oct means 8. So the octet rule says atoms want to have 8 electrons in their valence shells. This is a really powerful rule. I mean, it would be more powerful if more things followed it, but all the ones we're going to deal with will follow it, so it'll be really nice. It's a great rule because it allows you to predict what kind of ions atoms will form. So we know that atoms gain or lose electrons. This allows us to predict how many they will gain or lose. So I'll give you an example. Sodium. Anybody remember the symbol for sodium? Na, good. So how many electrons does sodium have? 11 electrons. How many valence electrons does sodium have? 1 valence electron. So if you had to guess, when sodium becomes an ion, a charged particle, when it loses or gains electrons, what's likely to happen? Yeah, it's going to lose this valence electron. Why? Why? Because there's just one there. So let's look at that diagram of the electrons again. Here are our 3 energy levels, our 3 buckets for electrons. We've got to put 11 in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, because we can only fit 8 in there. So if this one leaves, just erase it. How many valence electrons are we left with? How many valence, though? 8, right? And that's that full shell. That's an octet. So this is now a configuration for sodium +1, the +1 ion, because now we have one more proton than we do electrons. We had 11 protons and 11 electrons. We lost an electron. Now we have 11 protons and 10 electrons, so there's an extra positive charge there. But by doing that, we now have 8 electrons in the valence shell instead of just 1.
Why did that one valence in the third shell or whatever, what happened to that?
Yeah, good question. It doesn't just sort of disappear into nothingness. It gets transferred to another
shell?
Another atom of some sort.
Oh.
So maybe something else that's around, a hydrogen or a chlorine or whatever is floating around in the air.
So we always subtract like the one floating valence electron through the
Yeah, or like in the previous example, if we go back to magnesium, instead of losing 1, it loses 2. Because it has 2 valence electrons, loses those 2 to get that full valence shell. So I want to show you the other computer here. So I want to show you what it looks like when this happens. I would show you in person, but you'll kind of see why I don't do that. So if you go to YouTube or something and you look up sodium and water, you can actually see sodium losing its electron. After we skip our advertisements here. So there's our sodium. You can see, let me turn the lights down so you can see this a little bit better. So he's got this sodium in his hand. It's a big chunk. It is a metal. It is shiny, but it looks kind of. If we go back here, we can see that it kind of looks white, like kind of powdery almost on the outside. That's because it's what? No, this is sodium, pure sodium, just the sodium metal. It is a metal. It's a shiny silver metal, but it is, in this case, already oxidizing. It's reacting with the air to make this white stuff on the outside. If you cut it with a knife, what you see is kind of shaving off some of that white stuff. It's actually a shiny metal inside, and it's so soft you can cut it with a butter knife. So they're going to throw it in this pond.
That's fun.
And we'll see what happens. Professional camera work here.
Seriously.
All right, falls in the water. Start smoking a little bit. Yeah, so
Sodium.
So what you see there is the sodium. The reason it's delayed is because of that oxide. So what's happening is the oxide is kind of preventing that contact. It's sinking down in the water, and then it's starting to give its electrons away to the water. So it gives its electrons away to the water, and in doing so, it creates hydrogen gas. It turns the H2O into hydrogen gas and some other stuff. So then that creates heat because it's becoming more stable, so it's losing energy. It's exothermic, right? Losing energy. And that heat then ignites the hydrogen gas, and that's why you see the big explosion. So I would have liked to show you that here, but obviously I'm not going to do that. We can expect all the elements in that column then to behave in the same way, to lose that electron very easily and very exothermically. And we can, I'll skip around a little bit and show you a couple examples of that. This one we get some music. So you can see lithium first, just kind of buzzes around, catches a little bit of fire. We've got sodium, which we just saw. Very small amount now. We're just in a laboratory kind of environment. So same thing. It's burning. It's giving off. So that's kind of a smaller scale thing of what we saw in the pond. But you can see it's very easily and very quickly losing that electron, and it's creating a lot of heat because it's going to a much more stable situation. Now, as we move down the periodic table, this music is kind of annoying. Let's see if we get to the... Yeah, so there's just like one drop hitting it. And then they actually quote the video that we just watched, so we'll skip over to potassium. And you can see, like, as soon as he drops it in the water, it just explodes. And remember, there's two more below that.
It didn't even touch the water before.
Yeah, it's like, these are pretty much, you can't really do this. I mean, somebody did this, they recorded it, and then everyone else just shows it because nobody actually wants to do it again. Cesium, yeah, I mean, he put like a tiny little, barely visible amount of it in that water. And now you can see it in a bathtub, and it just totally obliterates it. Cesium's actually, I've worked with it quite a bit in graduate school. It's really a beautiful element. It is a gold liquid. So it kind of looks like mercury, like it flows, but it's gold. It's a gold liquid, cesium. So francium you can't actually do because it disappears in 22 minutes, so you can't actually find it. So we won't bother with that. There is a video in here somewhere. You can look for it if you want to look for some of those original ones that were quoted in that video.
Have you seen Breaking Bad by any chance?
No. I watched part of it.
There's a scene
But
in
then
a
I
bathroom
didn't
in a
finish it.
tub, just eating away something. It was,
He uses,
yeah, what was that?
they're trying to like hide a hidden body.
I did see that, yeah.
Wasn't it the blood that was like all over the place that he was trying to do?
Yeah, because he told them to just get a plastic tub and put the body in because the chemical would eat through it.
Right.
Put it in his bathtub and just like.
Yeah, I did see that. That was really pretty early on.
Yeah.
Right, I think that was before I
The
stopped
first season.
watching it. Yeah, the hydrofluoric acid was the chemical HF, which is a really dangerous acid. We'll get into that in the acid basis chapter. It's just hydrogen bound with fluorine. It's so dangerous that it dissolves pretty much anything. It's like, I call it cartoon acid. Most acids like we work with in lab, you've worked with them. They're there, they do some stuff, whatever. But HF has that cartoon acid behavior, like in cartoons where you drop acid on the floor and it eats through like 3 floors. HF will do that because it dissolves silica, and rock and tile and ceramic and brick and all that stuff is made out of silica, and this stuff actually eats through that, as well as bone. So I think they were using it to dissolve a body, and so it would dissolve the bones, but also it dissolves the porcelain that the bathtub is made out of. So it doesn't dissolve plastic, so it can't react with the plastic. Yeah. So if we work with HF, I mean, we won't in this class. I don't even think we have any in this building. It's actually, you have to keep it in plastic containers, plastic jars, or steel, because it won't react with the plastic or the stainless steel, but it will react with glass. It will actually eat right through glass. Yeah. So that's what that was. not an explosion, but just something dissolving. All right, so you can see how easily that can lose its electrons, which we predicted based on the electron count. So let's look at the other side. We know about sodium chloride, that's salt. So let's look at what happens with chlorine. How many electrons does a chlorine atom have? 17. And how many valence electrons? 7. 7 valence electrons is in column 7A. So chlorine, if we get its electrons here, we can put in the 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So then, by the same logic that we did with sodium, is chlorine likely to lose those 7 electrons to have a full valence shell? Possible, but there's actually an easier way it can get a full valence shell. Yeah, it can get one rather than give one away. So we can put an 8th one here to get a full valence shell, and then what's the charge on that chlorine? It's going to be -1 now, because now we have one more electron than we have protons. So we call that ion chloride. We'll talk about naming a little bit later. That's chloride, and the chloride ion also has a full valence shell, so a full octet in its valence. And this is one reason why sodium and chlorine react so well together. Sodium can give up an electron, chlorine can take the electron, and so now each of them is happier. And if we look at the behavior of these elements, we really see that. So we saw that in the video, that sodium, the atom, is really unstable, explosive. Sodium, the ion, is totally benign and does nothing. I mean, it's important, but we eat it, and it's in our bodies, and it's in everything, and it doesn't react with things. Same thing with chlorine. Chlorine, the atom, is super reactive. It's chlorine gas. It's a poison gas. And it can also be really easily burned or be really easily reacted with other things. Chloride, the ion, is in our bodies, is in salt, is totally harmless and just kind of doesn't react with anything. So by changing the electron counts, we go from a really unstable situation to a really stable situation. Now, if you look up at the periodic table, we can kind of predict this without having to count all the valence electrons by recognizing where the most stable atoms are. So what are the most stable atoms on the periodic table? Yeah, where are they? Right, group 8A. All those atoms, those are called the noble gases. They're really unreactive, they're really stable. And why do you think that is? Yeah, they have 8 in their valence shells already. So they don't want to react with things. They don't want to take or give up electrons. They want to stay where they're at. And that makes them especially stable. So the other atoms, we can think of them as being closer or farther away to the noble gases, and then we can figure out what the charge is likely to be. So let's look at oxygen. Oh, number 8. It has 6 valence electrons. It's 2 away from the noble gases. So what do we expect is going to happen? Right, that oxygen will get 2 electrons to go from 6 to 8, and we can kind of count it on the periodic table. If it gets 2 electrons, then that moves it kind of over by the noble gases. So we can talk about the atoms wanting to gain or lose electrons to get them closer to the noble gases. If we go to sodium, which we just talked about, number 11, you can say, all right, well, sodium could gain 7 electrons to go over to the noble gas, or it could lose 1 and go back to the previous one. Whichever one's closer is what's more likely to happen. So it's going to lose that 1 electron to become more stable. So questions about that so far? Or how we talk about that? All right. What we can do from this then is we can predict the compounds that these things will form together. And these things are called ionic compounds. Ionic compounds are just combinations of ions. So ions associated with each other. Ions, charged particles, we talk about ionic bonds, but I really like to save that term bond for later when we talk about covalent bonds. So really they just kind of get close to each other because we know positive and negative attract each other. So they attract each other, they stay together. That's really all there is to it. So when you have sodium ions and chloride ions together, you have a compound that we call sodium chloride, and we denote it as NaCl. So we don't actually draw the charges in when we're talking about the chemical formula for an ionic compound. But note, ionic compounds always have balanced charges. So we're not going to have NaCl2 or Na2Cl because that would make the plus and the minus no longer even out. They would no longer be balanced if we did that. So what if instead of sodium chloride we look at sodium oxide? Oxide is the ion made from oxygen. And what did we decide would be the charge on that? Negative, how many? 2. We can either put the negative before or after the 2, it doesn't matter. So if we know that oxygen is O2 minus, or O minus 2, because it wants 2 electrons to get to 8, and we know sodium is Na plus, what's the formula for sodium oxide?
Well, is it balanced because the oxygen's negative?
Yeah, well, yeah, so oxygen is 2 minus, sodium is plus 1.
Okay.
So they're not quite balanced yet, because if you put one of these with one of these, you still have 1 minus left over.
So how can
So what can you do?
we need to double this sodium?
Right, so we need 2 sodium atoms, or ions, for every 1 oxygen ion. The way we write that formula then is Na2O. So we put a little subscript 2, a little 2 below it, saying that we need 2 NAs for every 1 O. Let's try another one. Also, by the way, we'll talk about how to come up with these names also. That's for later. Magnesium chloride. Let's see if we can find the formula for magnesium chloride. What we need to do is we need to find the ions, and then we need to figure out how to balance them out. So what's the formula? What's the symbol for magnesium? Anybody know? Mg, right? So what ion is Mg likely to form? Mg2 plus. We talked about that one a little bit earlier because it wants to lose its 2 valence electrons to have an octet in the valence shell. And then chloride we just talked about takes a minus 1. So how do you get those to balance? So you're going to have 2 Mgs for every 1 chloride? So if you got 2 Mgs, how much positive charge do you have total? 4. So that's not quite right. What should we do instead?
Magnesium 2 Cl.
We need 2 of these instead of 2 of these, right? Now we have 2 minus total and 2 plus total. The way we write that...
Is this going to be on the test?
No. This is the next test. I mean, it'll be on the next test. It's not like you just don't need to know this. But this will be on the next one. Yeah, so we've got MgCl2, 2 Cls for every magnesium. Did you see how that works? Balance these charges out.
2 negatives equal a positive. The
2 negatives
Cl-
equal a 2 positive.
2 positives.
Yeah, so you got 2 plus and total 2 minus.
Okay.
And those have to balance out. All right, let's see if you can get another one. Aluminum oxide. What's the formula for aluminum? Al. So now we got to figure out what the charge is going to be on Al, what the charge is going to be on oxide, and figure out how to put those together. So see if you can do that one, and then we'll look at it together. Oh, we can turn the lights back on too. You got an idea for this one? No ideas? Well, okay, you're getting close.
AlO2.
Let's look at the ions first. So we know oxide is what kind of ion? 2. What about aluminum? Better figure out. How'd you get +1?
Well, it's on the third campus, so it's gonna be like, we have to get 1 electron out, so it can be blue.
All right, so if it has 3 valence electrons, right, and it loses 1, how many valence electrons does it have left? Still 2. So it's not full yet because it still has 2 valence electrons. We need 8 for it to be full. Let's look at it. So here's our aluminum. How many electrons total? 13, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 3 valence electrons. But what do you think is easier? Aluminum has to get to 8 valence electrons. What are the 2 ways it can get to 8 electrons? It could lose 3, or what else could it do?
Isn't there a role where it's more likely?
It could gain 5. So what are you going to say?
Isn't there a role where it's more likely to happen? It doesn't happen. Isn't like 4 or 5 the number where it'll keep its electron.
Yeah, usually the fewer electrons have to move, the better. So if it's got 3, it's going to be more likely to lose those 3 than to gain 5, because that's more electrons.
So if it's got 4.
If it's got 4, it could go either way. And so we see carbon and silicon in column 4 and germanium kind of going either way. Now, the more metallic an atom is, the more it tends to be positive. You'll notice all of our positive ions are metals and all of our negative ones are nonmetals. So when you get down that column, you can start assuming that it goes positive because they're metals. But you're right, you could kind of go either way. So we're going to lose these 3 from aluminum. And if we lose 3 electrons, we got an octet. And what's the charge on aluminum then? If we lose 3 electrons, our charge is 3 plus. Whoops, but it's not just A, it's Al. Because now we still have the same number of protons. We still have 13 protons, but now we only have 10 electrons. So we've got an extra 3 and extra 3 plus in there. All right, so we've got Al3 plus and O2 minus. How do we get those to balance out? 3 plus and 2 minus, that's going to be a little bit tough, right? So what do we do?
Balance them.
To balance them, because we need an overall neutral ionic compound.
So every oxygen one.
Well, if we have it 1-to-1, then it doesn't balance because you got 2 minus and 3 plus. So how do we get the minuses and the pluses to balance?
Do you have
Electrons from oxygen.
Oh, we can't change electrons anymore. Those are just our ions. We're stuck with those. We can only change the quantities of the 2 different ions of the ratio of the ions. A little bit of a trick to it. I just want to see if anybody sees it. So if you leave one at 1 and you leave the other and you only change the other one, you're never going to get them to work out, right? If you leave the aluminum at 3 and you take, let's say, 2 oxygens, well, now you've got 4 minus and 3 plus. That's not any better.
What about making the aluminum negative?
You can't change the charge. Charge is the charge.
You do 2 aluminum and then 3 in the oxide.
Yeah, that works. So if we take 2 aluminums, what's our total charge, total positive charge? 6, right? So total we've got 6 plus. And then if we take 3 oxygens, what's our total negative charge? 6 minus. So now they balance. The way we would write that formula then is Al2O3. So whenever you see this kind of situation where it doesn't, like, moving one doesn't seem to make it balance out, it means you have to move both of them and get a common factor, or a common multiple. A common multiple. So, a little tricky, huh?
Can it also work if you just multiply 3 by 2?
Yeah.
Right?
Yeah. Okay, that's kind of a good stopping point. I know it's a little earlier than usual, but we still have a quiz to do. So let's take a break now. We'll come back, we'll do the quiz, and then we'll move on with some naming. So we'll start in, I don't know, how long of a break do you need? 10 minutes, 15 minutes? Yeah.
There is.
Quiz today?
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 When did you say that?
On Monday? Some people did not get that memo?
If it takes next week.
There's a test on Monday. Yeah, there's a test on Monday, quiz today.
Wait, you said we had a quiz on Monday?
No, we have a test on Monday.
I know, but like this past Monday.
Yes,
Last.
yeah, yeah.
You said we had a quiz today.
Well, I said it last week, but I think I reminded everybody on Monday. Probably, right? I must have said it at some point.
Could be an open quiz.
No, but you can have a calculator.
How many questions are on the exam?
On the exam, I don't know. I haven't written it yet. It'll be. I mean, going by last year's, nobody had any trouble with
How long is
time.
it?
What?
How long is it break?
How much of a time? How much break do you want?
45 minutes.
45 minutes. Really, you want to be here all night? Let's do 15 minutes, and we'll come back and take a quiz.
Is it like short answer or is it like?
The quiz today or the all different. So it'll be multiple choice. It'll be other stuff. I just noticed on Blackboard there are some practice questions for the exam, but my actual real exams are not on there. So I'll put my exams from last year on there, so you can see what they really look like.
Like before the test.
Yeah, like I'll just do it right now.
Sweet. What's this quiz on today?
The energy stuff.
No.
Stop.